Hello, welcome to another module in this massive open online course. So, we are looking at the signal processing or how to process the received signal at the receiver of the digital communication system, alright, and we have seen basically the signal component and the noise component of the output signal after it is passed through the receive filter, alright. Now, let us characterize the noise power. What is the power of the noise at the output of this filter with impulse response HT. Okay. So, in this module let us start looking at how to characterize the noise power. So, we have characterized the signal power. Now, naturally I have to also look at the noise power, because remember ultimately I want to look at the signal to noise power ratio, which we said is an important metric to characterize the performance of the digital communication system. Okay. And in this regard what we have seen is that the noise, first let us look at the noise n is given as integral minus infinity to infinity n t minus tau. Let me just write it exactly using the notation that we have used, n t minus tau h tau, small n t minus tau and this we said is the noise, this is the noise component at the output, this is the noise which I am denoting by small n, or let us not denote this by small n, let us simply denote this by let us call this as n tilde. Okay. So, this is the output noise. So, this n tilde is noise after, so noise, so this is basically your noise after passing through the receive filter and sampling at t equal to capital P. So, this is noise after and sampling at t equal to capital T. Okay. So, now what we want to do is we want to calculate the noise power. Remember the noise power is assuming all real quantities, noise power is expected value. So, technically I have to write expected value of magnitude n square if the noise is a complex quantity, but assuming all real quantities here, for again once again for simplicity of analysis I am going to simply write this as n square. Okay. So, this basically is assuming, again I am just describing each aspect carefully so that you understand that this is for a special scenario with real elements or real quantities, real elements or quantities. Okay. Assuming all the quantities are real. Okay. Now, in order to simplify this, I am going to make a simplifying assumption. We are going to now go back to the most popular assumption, or the most one of the most relevant assumptions that can be made regarding the noise, that is the noise, as we already seen, typical noise random process is Gaussian, it is additive, white, Gaussian. Alright. So, we are going to assume that this noise Nt is additive. So, at this point, so what we have done up until this point does not depend on the specific nature of the noise, alright. The noise which is additive, right, passed through the receive filter and then sampled. But now to further simplify the noise power, I am we are going to invoke the popular assumption that the noise is white and Gaussian in nature, which means, so we are going to assume now, invoke the assumption that noise is white and Gaussian. We already see noise is additive. So, this is additive white Gaussian. So, noise is white plus Gaussian implies now with, and also we are going to assume that the noise expected value of NT, the mean is 0 and expected value, since the noise is white, we are going to assume that expected value of NT into NT plus tau is eta naught by 2 delta tau, right. With we have seen that if the autocorrelation is eta naught by 2 delta tau, that is an impulse. Also, therefore, the power spectral density, which is the Fourier transform of the autocorrelation, is flat over the entire frequency domain, and hence this is known as white noise, because the power is uniformly distributed across all the frequencies. Okay. So, we have already seen this in the previous modules. Okay. So, now this noise has 0 mean. So, this is the 0 mean. Okay. Also something to keep in mind, we are assuming that the noise is 0 mean, that is a typical assumption, noise is 0 mean, and it has it has basically the autocorrelation. This is basically your nothing but your autocorrelation function, remember, and for this, remember, we are assuming the noise to be wide sense stationary. Since the noise is Gaussian, wide sense stationary directly implies strict sense stationary also, but anyway, for the purpose of this, wide sense stationary is, purpose of this analysis, wide sense stationarity is sufficient. Now, if you can look at this noise, now let us go back a little bit and look at how this noise is obtained. Let us just recap a little bit. I have noise, correct, in the noise at the receiver, the thermal noise at the receiver, which is passed through this. Okay. So, that at this point you have minus infinity and t minus tau h of tau d tau followed by sampling, correct, followed by, so this is your, let us call this as n tilde t followed by sampling. So, therefore, this will be n tilde of tau, sampling at t equal to tau. So, this is your n tilde of capital T, which is calling as n tilde, all right. Okay. Now, the first thing that you have to realize is, well, of course, we have said that this noise is input noise process is Gaussian. This is an LTI system, that is linear time invariant system. So, it performs a linear operation. So, this is an LTI system. And we assume that the noise, input noise is Gaussian, or it is a Gaussian random process, or it automatically implies that noise is a, when I say Gaussian, it automatically implies that the noise is a Gaussian random process. Now, the first important thing that you have to realize is you have a Gaussian random process which is passed through a linear system, a linear time invariant system. When a Gaussian random process is passed through a linear system, the output is also a Gaussian random process. This is a very important. Any linear transformation on a Gaussian random process results in an output Gaussian random process. That is the important thing. So, therefore, this noise process n tilde t is also a Gaussian random process. That is the most important thing. This is also a Gaussian random process. Filter, since the filter is a linear system. So, input random process is Gaussian, pass it through a linear system, output is Gaussian. Remember we said if the random process is Gaussian, that is when the output random process is Gaussian, the meaning of that is statistics, right, joint statistics at all times are basically Gaussian, and therefore if you are sampling at this time t equal to capital T, right. So, joint statistics at all times are Gaussian, in particular at any time instant if you consider the noise sample, that is Gaussian, in particular if you consider the sample at t equal to capital T, that is also Gaussian, and it is a single sample, therefore it is a Gaussian random variable. So, you take a Gaussian noise process, you sample it at a single time instant, what you get is a Gaussian random variable. Okay. So, what we are saying is input noise process is Gaussian, it is passed through a linear system, therefore output noise process is also Gaussian, you are sampling it at t equal to capital T, you are considering a single sample, and therefore the sample is a Gaussian random variable, that is the most important thing. So, this sample n tilde, in fact we have justified that this sample n tilde, this is Gaussian random variable, okay, since it is a sample of a Gaussian random process. Since it is the sample of a Gaussian random process n tilde t, we already argued that n tilde t is a Gaussian random process. Okay. Now, therefore, n t or n tilde, which is minus infinity to infinity n t minus tau h of tau d tau, this is Gaussian in nature. For a Gaussian random variable, remember it is characterized by the mean and variance. Any Gaussian random variable is characterized completely by mean and variance. Now, let us see, let us ask this question, what is the expected value of n tilde, what is the mean that is expected value is nothing but the average or basically mean. What is the expected value of n tilde? Okay. Now, to answer that, look at this, the expected value of n tilde equals the expected value of minus n infinity to infinity n t minus tau h tau d tau. Now, expectation operator is linear, so I can take it inside the integral. Since the expectation operator is linear, integral comma integral expectation and integral are linear operations. So, this implies basically this is equal to, so can take the expectation operator inside the integral, and then you will see something very interesting. You will have expected infinity to minus infinity, expected value of n t h tau d tau. Now, you will realize that I am not using the expected value for h expectation for h of t, because this is a deterministic quantity. Because the receive filter is a fixed quantity, it is a deterministic quantity. Deterministic means basically it is a fixed quantity. Now, we have seen that expected value of n t is 0, the noise process is 0 mean, so this is 0. Since n t is a and therefore this is 0, integral of 0 is basically 0, and therefore what you get is basically this quantity, which is basically your mean of n tilde. It is very simple, although you might have realized it even without this elaborate derivation, but just for the sake of rigor, mathematical rigor and formality, we have shown that this expected value of 0 mean, expected value of n tilde is also 0. So, so n tilde is a 0 mean random variable. So, naturally if you take a 0 mean random process, correct, that is a random process which has an average value of 0, pass it through a linear system or apply a linear transformation on that, then the output will also be a 0 mean. Alright, output will be a 0 mean random process, you are sampling it at t equal to capital T, and that will be a 0 mean random variable. Okay. So, this follows naturally, although we have also proved it, verified it rigorously, since the expectation operator is basically linear. Okay. Now, the second aspect, the more important point is the variance, which is the noise power. That is the more important and more interesting thing, that is how do we find out what is the variance. The variance, or basically this gives us the noise power. What is the variance or noise power? To do that, let us compute expected value of n tilde square. So, we have expected value of n tilde square. I am going to write it as expected value of n tilde square. I am going to write this as expected value of n tilde times n tilde, just for the sake of convenience, because it helps me. Now, I am going to write it expected value of n tilde, that is integral minus infinity to infinity n of t minus tau h tau d tau, this is 1 n tilde, times I am going to just simply change the variable of integration, the integral remains unchanged, n t minus tau tilde h tau tilde n tilde. You will realize that this is also n tilde, which I have obtained by simply change of integration variable. So, that does not change the quantity. So, simply okay, I can call it tau or tau tilde, it will yield the same integral. But now, let us now simplify this product. Now, I can simplify this product as, now I can write it as a double integral, that is very interesting. I can write this as the double integral expected value of minus infinity to infinity minus infinity to infinity, well, n of t minus tau, n of t minus tau tilde into h of tau into h of tau tilde d tau tilde. Okay, this is what I can write it as. I am bringing both the integrals together, I am clubbing the integrals. Okay. So, evaluated as a double integrals, putting the integrals together. Okay. And now you will observe something interesting. Now again we are going to use the property that the integral is a linear operator, so I can take the expected value inside the integral. And again realize that n t minus tau and n t minus tau tilde both are random, but h tau and h tau tilde, these are deterministic quantities. So, the expectation operator does not apply to them, okay, because these are fixed quantities, h of tau and h of tau tilde. Okay. So, naturally I can take the integration operator. So, h of tau and h of tau tilde realized, and it goes without saying that these are fixed quantities. Therefore, I have integral minus infinity to infinity, applying it only to n of t minus tau, n of t minus tau tilde h of tau tilde d tau tilde. Now, you will realize something very interesting. Here this is nothing but the autocorrelation, correct. This is basically nothing but the autocorrelation nt minus tau tilde. And you realize that expected value of nt plus tau is equal to eta over 2 delta tau. That is, it depends only on the, that is what we have seen, and we already said this many times before, the autocorrelation depends only on the time difference tau, on time difference tau. That is the property of the wide sense stationary process. It depends only on the time. So, therefore, this, if you look at this expected nt minus tau into t minus tau tilde, this is nothing but eta over 2 times delta difference between both, that is delta of tau tilde, delta of tau minus tau tilde, or tau tilde minus tau, both of them are one and the same, delta of tau minus tau tilde. Okay. That is the interesting. So, we have used the property of the wide sense stationarity of the noise process n to simplify this quantity expected value of n capital T minus tau into n capital T minus tau tilde. That is simply nothing but eta over 2 times delta the time difference, that is t minus tau, that is t minus tau tilde minus t minus, which is basically tau minus tau tilde. Okay. So, basically it depends only on the time difference, and that gives us something very interesting. Now, when you substitute that, you will immediately see that you get something very interesting. So, what you get is, well, it tremendously simplifies the integrals. Whenever we have a delta function, you will realize, so h tau tilde delta, well, tau minus tau tilde, okay, delta tau minus tau tilde, okay, or you can also write this as delta tau tilde minus tau, because the delta function is symmetric. So, you can also write it as delta tau tilde minus tau d tau tilde d tau. I can also write this as delta tau tilde minus tau, delta tau minus tau tilde, both of them are one and the same, okay, it does not matter. Now, if you look at this, now if you look at the inner integral is with respect to tau tilde, okay. So, let us say inner integral is with respect to tau tilde, okay. Outer integral is with respect to tau. So, I can move h tau into the outer integral, minus infinity to infinity. Now, inner integral will be h tau tilde delta tau tilde minus tau d tau tilde whole thing into d tau. Okay. So, two integrals, separating it into inner integral and outer integral. Now, if you can look at this h tau tilde delta tau tilde minus tau, This basically can be simplified by using the shifting property. That is, if you have a function, the shifting property states that if you have a signal x of t minus t naught, x of t times delta t minus t naught dt, that is equal to x of t naught. This is what the shifting property tells me. So, this is known as the shifting property of the Dirac delta function. Okay, from your knowledge of the Fourier transform theory, you must know that this is the shifting property of the Dirac delta. Therefore, integral minus infinity to infinity h of tau tilde delta tau tilde minus tau d tau tilde, this is nothing but h of tau. This is follows from the shifting property. Okay, and therefore, now if you can look at it, h of tau into h of tau, that is nothing but h of tau square. So, what happens is inner integral is also h of tau by virtue of the function delta. Of course, there is going to be an eta naught by 2, I am sorry, I have missed the factor, but eta naught by 2 is a constant. So, that will come outside of the integral, no need to worry about that, eta naught by 2 is a constant. So, this is eta naught by 2 minus infinity to infinity, and what you have is something very interesting, h of mod h of tau square, or since all the quantities are real, you can also write it as h tau square, but we will leave it as mod h tau square just to also account for the general scenario. And now, this is nothing but, you can see eta naught by 2 mod h of tau square, this is nothing but energy of the filter. That is, I can denote this by E of h, right. This is energy of the filter, E of h, energy of the filter corresponding, that is the LTI system corresponding to the impulse response h of t. So, we have a very beautiful relation, the noise power is eta naught by 2 times the energy of the filter, that is eta naught by 2 times minus integral minus infinity to infinity magnitude h tau square d tau, which is also magnitude h t square dt, because the integral the variable of integration does not really matter. Okay. So, this is basically a very beautiful relation. So, what we have is, you have this, remember this is the quantity expected value of n tilde square. So, in fact, we can say expected value n tilde is a Gaussian random variable, this is the variance or the power, this is the noise power. Also you can say this is the variance of the, since this is a 0 mean Gaussian random variable, expected n tilde square itself is also the, this is the variance of n tilde. Therefore, the noise power at the output, we have a very beautiful relation for that, that is simply eta naught by 2 integral minus infinity to infinity magnitude, either you can say h tau square d tau or magnitude h t square dt integral, because tau or t is simply a variable of integration, it does not really matter. Okay, that is simply a variable of integration, that does not really matter. Okay. So, therefore, we have derived the noise power, that is noise power. Remember noise power at output of the sampler, that is after sampling, remember this is the noise power at the output of the sample. Okay. So, we have performed this analysis, and now what we have derived, previously we had derived the signal power, now we have derived the noise power, and to derive the noise power we have invoked a very important assumption, that is this analysis, remember, is not valid for any noise process. The assumption here is that the noise NT is a 0 mean additive, of course additive has already been assumed, it is a 0 mean white Gaussian noise. Okay. And this kind of noise, as I have already said, is one of the most relevant and one of the most practical models for the thermal noise occurring in systems, and is also a popular, very popular model noise model to be used, which is used to model the noise at the receiver in a digital communication system. So, this model is a very relevant model, and this gives us the noise power at the output of the sample. So, previously we have calculated the signal power, we have the noise power, we can calculate the signal to noise power ratio, and from that we will find the filter H of t, which maximizes the signal to noise power ratio, that is known as the optimal filter. Optimal filter in the sense something that is optimal, in the sense something it is which is the most suitable, alright, something optimizes something in the sense something that is gives you the maximum benefit or maximizes some parameter. In this case we are looking at the optimal receive filter HT, which maximizes the signal to noise power ratio. Okay, so that is what we are looking at. So, we will stop here and continue with this analysis in the next module. Thank you very much.